All right, looks like we've about made it. And it's official. Welcome back, folks. We're about to finish off our sixth week. And that means probably the biggest announcement is we're getting closer and closer to our second exam. Our second exam is going to be on Monday, the 13th. And so that means this Friday, I'm going to be working on posting the extent on exactly what's on exam two. I'm thinking probably a good extent for exam two is going to be sections 5.4, 6.1, and 6.2. 6.3, we could probably squeeze it on there, but I'm not trying to make exam two too wild or difficult. And this is probably the more technical section that we're getting into so far. But I'll make all that official on Friday, probably first thing in the morning. I'll be working on going to this spot of the Canvas page, filling out the information here, posting some exam review questions like we did on exam one. And after I get all that done, I'll be also over the weekend working on writing the second exam actually, and then sending it out to the various testing centers. So my hope is, and this will very likely be the case, first thing on Monday morning, I'll email every single one of you with instructions on how to contact and schedule the testing center and schedule your exam. So pretty much we're just redoing the cycle from week one to exam one all over again. We'll have another third exam and then a final exam to finish out the course. Oh, and by the way, one thing I keep forgetting to mention, we might as well just make it official by typing it in right here. A basic scientific calculator can be used on this exam. And this will be the calculator exam policy going forward on all the rest of the exams, exam two, exam three, and the final exam. I don't think exam two really uses the scientific calculator in any big way directly, but you might see it's a bit of a comfort, maybe just to test out reasonableness of answers and that kind of thing. That's pretty much my big announcement for the day. Any questions about the upcoming exam or otherwise to start us out? Okay, well, it's another exciting day of trigonometry. What makes the content today kind of exciting is graphing can be kind of tedious. It takes a lot of work. I have a humongous summary document of just the major methods on how we get it all done. And it took us a long time just to get through section 6.2. But after we finish off this, we're going on to other topics, looking into inverse functions. So let's get started now. Here's where we left off. We had just enough time to plot the tangent function. Maybe just a quick review before we get started. Plotting all these functions, you might notice, has a really big pattern. Whatever the function is for sine or cosine, for example, the first thing we saw was we want to calculate the period to start, which was just taking 2 pi divided by the b coefficient. We calculated the phase shift directly after, which was just changing the sign of whatever is here, dividing by b, and that formed the phase shift. Then we calculate the increment, where it starts, possibly where it ends, and the midline equation was only relevant to the sine and cosine problems. We didn't look into those too much for the rest of the problems. But this is pretty much the major core of what we were doing to plot everything. In section 6.2, we did the cosecant and secant functions. Cosecant is nice because it feels like the same exact steps. You just have to know how to plot cosecant based off this information. Secant is the first one that's a little bit troubling because whenever we have vertical asymptotes, our graph must start at that vertical asymptote when we graph over one cycle or one period. And so we had to use this formula to begin at the vertical asymptote. And tangent had that same problem. We take negative pi divided by 2, which is related to this 1/2 pi, just like the negative, I keep saying pi, excuse me, we take negative p over 2, p is the period, which is related to the increment, half the period, much like this is negative p over 4, coming from the increment of 1/4 of a period, 1/4 times p. And that's pretty much what took us to here. We drew this out by scratch. We noticed that the fundamental thing to start off the sketch is knowing where vertical asymptotes are. That organizes everything about the plot. So we get vertical asymptotes where cosine goes to 0. And that's why we started at negative pi over 2. The period of this happens to be pi. That's the distance from here to here where the graph starts to replicate. Notice we plotted this one over 2 full periods. And if you calculate pi over 2, you get to all the interesting locations. But critically, we started at negative p divided by 2, or negative pi over 2 altogether. If there was a phase shift, we would have had to add it to the graph, and that's how we got started. So every time we plot one of these, really you would do this first. Calculate the period. That's supposed to be the number 1. Second, you would calculate the increment, which is going to be 1/2 times the period. Already that's a little bit different. On all the other functions we plotted, it was 1/4 times the period. But this one's different. 1/2 the period is going to take you to the intercept, to an asymptote, intercept to asymptote, and so on. Then 3, you'll calculate the starting position, because that's already indicated up here. So 3, do that, figure out where your graph actually starts. And this would be the 4th thing you do. Draw a vertical asymptote. 5th thing you'll do is draw an intercept. 6th thing you'll do is draw another vertical asymptote. This gets redundant. The 7th thing you do is draw just the next intercept. 8th thing you'll do is draw the next vertical asymptote. And then finally, you'd probably would put the sketch down. It'll be this curve if tangent has a positive coefficient in front. Flip it if the coefficient is negative. And the final and easy thing to miss is the 6th thing is to plot this number on the vertical axis going up and down so that we know the scale in the vertical direction. But doing that, you always take halfway the distance from an intercept to a vertical asymptote. If you could go half that distance, you just put a point here, and that would have been a 1. If there was a 7 in front, we would have just put a 7 instead, and that trick always works out, which is kind of nice in a way. So our goal is to just review all of this all at once with the transformation of the tangent function. First, any questions before we give it a try? Okay, so let's work this through. The critical thing that's new about both tangent and cotangent is the following. Y equals tangent, y equals cotangent x as functions have period. We'll just write p for period as usual, just pi. And that's definitely a pattern break because everything else, whether it was sine, cosine, cosecant, secant, the period is what goes in the numerator here, 2 pi, then divided by b. So the period of just sine alone, don't know why I scrolled up there, period of just sine alone was 2 pi, same with cosine, cosecant, and secant. But over here with these new functions, the period is just pi for both. That means on our very first step, when we go to compute this, we'll say p for period, we're doing this part right here, period and phase shift of the function. It's going to be pi this time because we're dealing with the tangent. Divide by leading coefficient of x inside the function, 4. So that's the one big change already. After we do that, we'll go to phase shift. Phase shift, we take this whole quantity, flip the sign. That's always worth remarking. That's the easiest thing to forget. If it's a negative pi over 2 here, we'll flip it to positive pi over 2, and vice versa. Divide it by the coefficient of x once more, so 4 will go in front. And then just simplify it. This pi over 2 divided by 4 will give us pi over 8. So now we have a period, we have a phase shift. The very next step we indicated on our refresher problem was get the increment. But any questions to this stage, getting those two key elements? Okay, so here's the next thing that's different. It's always good to review how we did the other ones, like in the section 6.1 homework, for example. We calculated 1/4 pi here and here for sine and cosine. Same for the functions down below here, but tangent and cotangent are definitely different. We calculate 1/2 of the pi to get our increment out. I keep saying pi, sorry about that. We calculate 1/2 of the period p. So increment is going to be 1/2 times p. So this will be 1/2. Look up p, it was pi/4, giving us pi divided by 8. So now that we have the increment, we can determine where the cycle is going to start or where the period is going to start, get all of our points, and we'll be able to start to sketch this thing. One thing it says to do on this that's a little bit different as well is plot the function over 2 full periods. So really that's what we did right above here. This was 2 periods when we drew these sketches twice between the asymptotes. What that does for us is it makes instructions pretty much the same as the other ones. We need 5 key points. First one is going to be where the period starts. We'll just call this start. And it's much like the secant function. It has a non-standard starting position. To get to the very first vertical asymptote, we take -1/2 times the period p, add the phase shift. So we've calculated this, just not with the negative sign. Throw a negative in front of that, -pi/8. Add the phase shift. The phase shift is over here, pi/8 as well. And that tells us we're going to start this right at 0. Then next, the ending, because we're doing this over 2 full periods, is going to be where we started, 0 plus 2 times p. Well, the period was pi/4, so this is 2 times pi/4. Or if you like, you could write that as pi/2, that'd be just fine. If you're adding pi/8 to get all your values on the horizontal axis, the x-axis, you might want this in terms of eighths. So you could write this out as 4pi/8, just so that we could do a rough check as we're adding pi/8 over and over again. Well, that's all the scratch work we do before we even get started. At this point, it's just a matter of plotting the tangent function. Any questions at all before we start this out? Okay, so here's how it goes. First, we begin with the horizontal line. We're starting at 0, so I'll emphasize quadrants 1 and 4 primarily. The starting was right at 0, but that's always going to be first a vertical asymptote. We want to sketch the vertical asymptotes using the dashed lines. We're also marking the exact positions of the x-intercepts as we go. And then we just have to remember to also label the y-axis, but let's go in order of the instructions. Pretty much I try to write the instructions in the order you'd want to do all this stuff to get a plot in as most organized and rapid way possible. So vertical asymptote to start. Then we increment to the next key location on the graph, which is going to be at pi/8. But for both tangent and cotangent, that takes you immediately to an x-intercept. That's kind of nice. Then keep on adding pi/8. We're at 2pi/8. Notice it's the same strategy as way back in section 6.1. Once we have the increment, we know where all the interesting locations are on the plot. And for cotangent, at the third point, we have a vertical asymptote. So this will go like that, and then just repeat the pattern. 3pi/8 is an intercept. 4pi/8, which you can reduce to pi/2 if you like. I typically, you probably notice, just leave them right in that format on the x-axis so that reducing fractions doesn't seem to compete with the larger concept of actually plotting the trig function. So all the values are down. We also want to label the y-axis, but that's not too bad. Whatever this number is right here, once we put the plot down, we'll just come back to this and label that axis. Let's go with a slightly different color. Want to box that out in a way that doesn't kind of disrupt what the function looks like. Now we're about ready to start plotting the tangent transformation we see here, but we want to do one additional thing. Another strategy that I saw people do on their homeworks as well, section 6.1, is just write down the basic shape for tangent. Y equals tangent x has this as its basic shape. It starts with a vertical asymptote to the left of the y-axis, intercept in the middle, another intercept here towards the right, ending on a vertical asymptote. And the key information we want to know about this is tangent itself is an increasing function, so it goes like this as a rough sketch. And last thing we can throw on here is if we go midway between an intercept and a vertical asymptote, we get a point here that produces the value 1. Our value is going to be 5, but we're just going to repeat that strategy as well from over here. Really, this is just a quick and dirty version of this in its full detail that we plotted earlier. So now we'll do the task of actually plotting this function. 5 tangent 4x minus pi over 2. Maybe one more comment. If that was a -5, we would have drew a graph under it where we just flip this whole thing. But it's going to look like the same basic shape. It'll come up through the intercept and then up again. Usually you don't want it to connect with the vertical asymptote since that's algebraically impossible. So something like this would look like a better graph. I'm not super picky. If you have all the right elements, then you'll get full credit. If you did something like this, that could lose us points because it seems we didn't really understand that that was a vertical asymptote. But again, it doesn't have to be like machine plotted perfect. So do your best freehand sketch. They should be identical, but just do your best to draw as identically as possible. And the last thing we need to put in is some information on the vertical axis to indicate the scale in the y-axis direction. But we're just about there. This one, again, it looks different than this, but that's just because we had a phase shift that was involved with it as well. But it's the same kind of idea. You can go midway between an intercept and a vertical asymptote, any vertical asymptote. Maybe you put a point here, or maybe you put a point there, maybe you did both. And just like we see here, once you put a point down, you can come up, hit a point on the curve, and then go immediately to the left. That's going to be at height 5. If you used this tick mark, you would go down to a point here, and that will be at height -5. And that does it for us, folks. This is the complete sketch of this interesting transformation of tangent. Any questions at all with any of those features on how we built the curve? Okay, maybe one last comment. There's a kind of a cool check that goes along with this. If we put everything right, the positions of all the values on the x-axis, the y-axis, if the curve looks about right, then one pretty good check is actually say what this number is. It's between 0 and pi over 8, so that would have been pi over 16 on this problem. You might have to take an average if it's not as convenient to compute like we did here. So if you had that extra time available to you, maybe just a little bit extra time after doing exam 2, take the pi over 16, and this graph tells us it should valuate to -5. So let's test that. Take this, y equals 5 tangent, 4 times the input value for x, which is pi 16ths, minus pi over 2. So that's what this whole function would say to do. And then when we start to simplify this, it's 5 tangent. Let's reduce this fraction. 4 times pi 16ths is just pi over 4. Minus, we want this to have a denominator 4 now, so multiply by 2 over 2. So 2 pi over 4. So now it's 5 tangent. Negative pi over 4. We can cite the unit circle now at negative pi over 4. We are here in quadrant 4. Tangent happens to be negative here. The sine value is negative root 2 over 2. The cosine value is positive root 2 over 2. So this is 5 times negative 1, coming out as a negative 5. But that's exactly what the graph is conveying here with that tick mark at negative 5. This is in orange just to emphasize it's just an additional check, not something you have to do. But if you had additional time in an exam setting, maybe on exam 2 or the final exam, not a bad thing to just look into to see if it works out. Well, our next function, the last 2 problems of this entire set of notes, is going to be looking into the cotangent function. But really that just means we're essentially doing exactly what we did before. We're just flipping it around because if cotangent is the function we're dealing with, that just means cosine is in the numerator. So different vertical asymptotes, different shape to the curve, it's no longer increasing, but everything else goes exactly the same. So it's like good practice of the prior problem in a real sense. So let's start this off. This is the final one for our entirety of plotting techniques in this semester, so congratulations, we're almost there. Y equals cotangent x can now be expressed as cosine x divided by sine x. And we can say that this function has vertical asymptotes where the denominator, sine x, is exactly 0. Sine x equaling 0 implies immediately x, well, it could be 0 itself. Sine of 0 is 0. It could be pi, but it could also be negative pi. So we convey that by just saying plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Every multiple of pi, integer multiple whatsoever, is going to give us a sine value of 0. And so that's the location of every vertical asymptote. The next thing about this is it starts right off at 0. So we don't have to move backwards by half a period divided by 2, negative period over 2 to start the cycle. Whatever the phase shift is in the problem, that's where the cycle or the period was going to start. And that's typical for almost every function except for these 2 odd ones out. Anytime cosine is in a denominator, it causes these 2 different formulas that we need to be aware of. So with that information in place, here's what the sketch is going to look like. Starting with a y-axis here, we immediately get a vertical asymptote overlapping the y-axis. Standard thing to do is just to trail it off like that. That shows there's a vertical asymptote there. Then we can say go off to the next vertical asymptote. We'll go in the right direction, so we'll just go off to pi. Next vertical asymptote at 2 pi. And that would be 2 cycles already, or 2 full periods. So next vertical asymptote, once I get my controls to work, there we go, is right at pi. And final one is right at 2 pi. Now we expect by the blast plot an x-intercept to be exactly here, right at pi over 2. Another x-intercept to be exactly here, midway between pi and 2 pi is 3 pi over 2. But you know, that should make sense if we just think of evaluating the cotangent function. Cotangent at pi over 2 gives us cosine at pi over 2. Divide by sine at pi over 2. Sine at pi over 2 is 1, but cosine is 0. And that gives us 0 altogether. So that tells us, yeah, that's right. We do have intercept right here. Cotangent 3 pi over 2 is 0 as well, since cosine 3 pi over 2 goes to 0. So we have a 0 value there at the same time. Last trickiest thing to decide is the curve increasing like tangent was, or is it decreasing, doing something a little bit different? But we can determine that pretty quickly as well. We can take this value. This will be pi over 4. And this value between pi over 2 and pi is 3 pi over 4. And just evaluate cotangent on those 2 points, and we'll get some great information. Might not be a bad idea to even throw in a unit circle on there. Why not? In fact, this comes back in section 6.3, which is kind of cool in a way. So here's pi over 4. Cotangent pi over 4 is just a 1, because cosine of this value is root 2 over 2, about 0.7 here. Sine of that value is also root 2 over 2. But then when we go to 3 pi over 4, both cotangent and tangent become a negative 1. Cotangent 3 pi over 4 is negative 1 in this quadrant, but that's just because cosine down here takes on negative root 2 over 2, whereas sine takes on a positive root 2 over 2. So we just get a negative 1 when we divide those. That told us everything we need to know. At pi over 4, we're at positive 1. So the curve should go through that point. And like we mentioned before, if there's like a 5 there, we would have just put a 5. And that's going to be midway between the vertical asymptote and the intercept. So same exact concept with tangent function. Then down here at negative 1, we have this point at 3 pi over 4. This is telling us now that the cotangent graph is a decreasing graph. Tangent increases, but cotangent had to be a little different. It's a decreasing graph. It looks about like this. Not the prettiest graph in the world, but you know, we are doing this freehand, so I'm going to let that one stand just to convey that is acceptable. If I try to do it a little bit nicer on this end, it might look about like that. It's probably the best one I'm going to draw all semester. So imagine that those are identical. Our imagination's important in mathematics sometimes. This is finally our plot of y equals cotangent x. We plotted over 2 complete cycles or 2 complete periods, which tells us already from here to here, that was just 1 period. So this matches what we saw with the tangent graph. Period is pi. Then another thing that's nice about this is we started right on vertical asymptote, right where sine the graph would have started itself. So the start is equal to whatever the phase shift happens to be in this problem. No additional weird parts of the formulas, like with the secant or with the tangent graphs that we got through. So this one feels like it's kind of a relaxing one to end the notes on. We'll do one more plot of a transformation of cotangent. But any questions or comments on how we built the core graph? Okay, so finally, here's the last one, example number 8. Essentially the same exact instructions as we saw in the last notes. We're going to plot this over 2 complete cycles. Notice the word cycles or period is completely synonymous. The book interchanges them pretty freely as well. Before we do anything with plotting though, the order of operations we would want to take is first get the period, then get the phase shift, the increment, the start, the end, then we could set up our axes. So looks like a lot's going on with this thing, but doesn't matter how complicated it looks, just follow the process. For the period here, P, we take the period of the original graph cotangent, which is pi, then divide it by whatever happens to be the coefficient of x, 1/11th in this problem. So this will be pi times 11 over 1. So 11 pi, it got stretched out by a factor of 11 if you divide by 11 into x. So period is done. It also moved around by an odd amount, pi 22, pi over 22. So the second thing, the phase shift, is take the opposite of this, negative pi over 22. Divide this by 1/11th again. Now this turns into negative pi over 22 times 11 over 1. So the phase shift on this one is going to be equal to negative pi over 2 altogether. So with those two pieces of information, next thing we want to get is the increment. So the increment in the plot takes us to all of the key values after we know the starting position. It is 1/2 times the period P. That's just for tangent and cotangent. It's always good to bring this up to compare and contrast. For everything else where it says also calculate, those are the increments, and it's 1/4 of the period for every single one of these. So it's just tangent and cotangent are the odd two functions out when it comes to getting your increment going. So 1/2 the period is just going to be 1/2 times pi 11 pi. So this is going to be 11 pi over 2. That's the value we have to add to get to all of our values. Cotangent is a nice forgiving function. The start is exactly whatever we said the phase shift is going to be, which is at negative pi over 2. Then finally, if we're plotting over two complete cycles, we need to know where we're going to end. So we'll write down the ending value is going to be, take your starting value, negative pi over 2, add to it 2 periods. Well, the period was 11 pi, so we're going to say that this is negative pi over 2 plus 2 times 11 pi. A little bit of arithmetic here. Negative pi over 2 plus 22 pi, and that means it's negative pi over 2 plus, multiply this one by 2 over 2 to get 44 pi over 2. Finally, looks like the worst thing about this is the fraction. Altogether, we have 43 pi over 2 is where this ends. We need to show the exact values on both the x-axis and the vertical axis for both the homework and the exam question. So working this out carefully is really helpful for us getting those values in exactly. I try to make it a little bit more manageable on a real exam question. But these are the 5 big components we wanted: period, phase shift, increment, the start, and the end. Any questions on doing this preliminary work? Okay, now we're going to set up those scales, those axes. Starts at negative pi over 2. So what I'm going to do on this one is really just first put down the horizontal x-axis. Then I'm going to put in the start, just way over here, negative pi over 2. Add 11 pi over 2. I'll get all my tick marks in, and then just put where the x-axis would end up after all the information. So add 11 pi over 2 to the negative pi over 2. We're at 10 pi over 2. Add it again, plus 11 pi over 2 is 21 pi over 2. Plus 11 pi over 2 to that is 32 pi over 2. Add 11 pi over 2 again to the last value, and that's 43 pi over 2. Here's where we do an internal check. That's exactly where we said it should end. And so this gives us great numerical evidence we're on the right track. The vertical axis, though, is going to be really close to about right here. It's kind of wonky, a little bit off balanced. Vertical axis goes here. And now we're ready to start sketching the whole plot. Whether it's a tangent or a cotangent, we're always going to start on a vertical asymptote. So that first tick mark at negative pi/2 led us to the first vertical asymptote. Increment was important because it led us, when we added 11 pi/2 to that, to the first x-intercept, right exactly here. Then add it again, and we got to the second vertical asymptote. And rinse and repeat. Next one is an intercept. Next one is an asymptote. So now we have essentially our grid lines where the cotangent function is going to be plotted. We need to look at this function really carefully, decide how it plots, but we have most of the information so far. So first, let's just write down the core graph or cotangent like we did in the notes above. If you're looking at y equals cotangent x, it looks about like this. Start with the vertical asymptote, intercept to the net asymptote, and then another intercept, another asymptote. This function was decreasing. So left to right, it's going down like this. But if you notice the wording in this problem, there's a negative sign. We need to reflect our entire graph that we're considering for cotangent across the x-axis. Or maybe you just have a really good visualization, a good mental chalkboard. You might not even apply this. But for me personally, I actually really need to see that, or I could get mixed up easily, especially if I'm flipping things around as well. So to do this as accurately as possible, and it just takes a second, draw down the second graph, y equals negative cotangent x. Still has the pattern with intercepts and vertical asymptotes. But the negative sign right in front tells us what was a decreasing function is now an increasing one. And our plot is going to look like this now. So if we can get that on paper just right, our job is also almost done. We just have to make sure we return to this part right here and actually label the y-axis. So first, let's plot this curve. It goes about like this on the x and y axis we plotted. Then another one. I kind of missed that x-intercept. And it looks kind of funny with it above the graph like that. I'll change it for the notes because that's kind of distracting. But if you did that on an exam setting, again, I'm not going to be super picky. I know you intended for it to go through like this. It just can't be something egregious, like totally going away from a vertical asymptote. Being way above or below intercept could be a problem. So the whole curve is there. And the final trick is to get the scale on the vertical axis, you take one value here, take this position here, and that would have been -1. If this was a -1/2 in front, we'd have written -1/2 instead. So that's where the role of this comes into play. This is going to either stretch or compress, this time compress in the vertical direction in addition to the reflection. So go halfway between -pi/2, 10 pi/2, roughly here. We take a value on the tick mark there. It's kind of hard to plot it in. We'll use the arrow method. That's at -pi/2. And then that means up here, that would be a positive pi/2. So that's us labeling the y-axis using the information from the function right here, the -1/2. Well, we did it, folks. That's the complete walkthrough of dealing with tangent and cotangent functions. It's a lot to take in when you see it for the very first time, but that's the purpose of doing these things in the homework. We do them in the homework. We're going to copy these instructions just like you see them here. We need the exact values of the positions on the horizontal axis as well as the vertical axis. Watch out for these instructions. Sometimes we're plotting over 2 cycles. Other times, like say in this problem up here, we're plotting over just one full period or one cycle. So we don't want to plot with the whole, say, like 6 intercepts. We just want something that goes like this on both the homework questions and the eventual exam question that will come up. There you go. There's the last one we ended on. Well, any last questions, folks, before we close out these notes and take a look into 6.3? It's actually taking a while to save this thing. Okay, once the computer gets through that, let's take a look into that next section. I've included a lot of supporting documents for coming up into the next section because there's a pretty good amount of technical information we need from the prerequisite class, Pre-Calculus 1. So there's lots of ways you could relearn this. Some people might be pretty fluent in inverse functions, and so this is probably you're going to get a good refresher when you just look into the notes in 6.3. I included some information from Pre-Calculus 1 on inverse functions that we need directly to get started. So if reading through these definitions and the theorems below ring a bell and you feel like you're pretty well refreshed on inverse functions, I'd say you do pretty well in this section, 6.3. But if it's been a while since Pre-Calculus 1, or maybe you took it in high school and it's been a number of years potentially, you might want to review it a little bit more just to get a good feel for what's going on in this section, or else it can feel like a pretty otherworldly, mysterious section when it wasn't intended to be. So this is a pretty great video here, about 15 minutes, I believe. This was like an organic chemistry tutor showing you how to deal with inverse functions. This is a document that I wrote from scratch. So if you'd like to see just information in a page or in that kind of format, that'd be great. And also, if you look into assignment 6.3, we're returning to problems in the book, but if you go to section 1.7 in our free textbook, that is the section on inverse functions. So you can do some pre-reading in the book as well, or skim through just for the sake of refreshing. And here's where it's going to start. After looking into some of that review information, maybe before we come back on Monday's class, we'll look into all of this information here with a goal of sketching the inverse to the sine x function. That's actually kind of challenging in a way. And we've done a lot of curve sketching. I said that's last section is going to be our last section on sketching curves, so it feels like a lie. But we're going to sketch this in a slightly different way by using technology. So it's not a numbered example. This is just us getting started, thinking about what we even mean by inverse functions. So let's kind of make this fit so we can see all the notes. We want to sketch the graph of y equals sine x and its inverse on the same axes, state the domain and range of both functions. So first, let's plot y equals sine x. There it is. We want to invert that function that you see right there, and that might be concerning depending on how refreshed you are on inverse functions. First, an inverse function, let's take a look here, is just saying that the function is invertible. So saying that you have an inverse function is saying the function is invertible in the first place. Your function has to be 1-to-1 in order for it to be an actually invertible function. Well, for a function to be 1-1, algebraically, it means this. If f of a equals f of b, that implies a equals b. But geometrically, it means your function has to pass the horizontal line test. Here's what the horizontal line test looks like. Plot a horizontal line. That one's kind of boring. It doesn't intersect the graph. So we look at other horizontal lines. Some horizontal lines, like this one, intersect the graph infinitely many times. Imagine that's a perfectly horizontal line. It intersects here, 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 and here, here, and here. So this function is absolutely not 1-to-1. Different values lead to the same inputs. The f at a would be this number. We can get to this number by whatever that x value is, whatever that x value is, and infinitely many more if we go to the right on this graph. It's a periodic function, so it keeps repeating. So it makes it seem like 6.3 is a short section, right? Sine x doesn't have an inverse, except we can force an inverse to get it to happen here. This is the same kind of thing when you try to take the inverse of y equals x squared. That function doesn't really have an inverse unless you restrict the domain to 0 less than or equals to x. Now it's invertible, and the inverse function is y equals square root x. And you can visually see their inverse functions because of this theorem down below. The graphs of a function and its inverse are symmetric about the line y equals x. Here's y equals x, and that's what symmetry about that line would look like. I'm zooming in just to see it a little bit better. Other information is if there's a point AB on one graph, then there's a point, I said that in a weird way. If there's a point AB on one graph, just switch the order of the x and y values, and the point BA is on the other graph, and vice versa. So even though if it doesn't look like the situation is nice enough, you can still invert your function, and that's what we're going to do. Take sine x, here it is on its big domain like before. We just want to find the longest domain we can for which that function is invertible. And there's lots of ways to do this. There's infinitely many choices. Here's one choice. 0 less than, let me try again, negative pi over 2 less than x less than, we can't go up to pi because already it's failed the horizontal line test. It intersects twice. If we go to pi over 2, we have a pretty good extent of the sine curve here, and it will pass the horizontal line test here. So this is the trick. If we want to invert the sine function, get sine inverse, we restrict the domain from negative of pi over 2 to positive pi over 2, excluding the boundary points. So the curve would look like this, or excuse me, I got that backwards, including the boundary points. Less than or equals to should actually be there. So that's the graph of sine x. If we want to graph the inverse function, its inverse, well, it has a lot of names. One way to call the inverse function to this is to write out arc sine. X is one name for the inverse. We put y equals x on there again. Notice we do have symmetry across the line y equals x. Let me turn off that graph so it doesn't get too busy. But the curve in black is arc sine. The curve in red is the sine function. I didn't need to specify the domain. It just gave us everything that we could use. This point here is at negative pi over 2, negative 1. And this point is at, flip it around, negative 1, negative pi over 2. So these coordinates flip around. For some reason, it approximates this one, but it didn't approximate to that one there. Who knows why? So again, the first problem of this is just a warm-up problem, thinking about inverse functions in the first place, and getting our first quick sketch of that. So here's what it looks like. So this is the arc sine function. We could also call it the sine inverse function. There's two ways to say the same thing. And this one is sine inverse of x. The other function over here is sine x. And essentially, we can see the domain and range right away. The domain of sine, it's not our ordinary sine. We've restricted the domain to force it to be invertible, but the domain of sine x here is from negative pi over 2 to positive pi over 2, and the range goes from negative 1 to positive 1. So we're at negative 1 here for the lower end, the minimum, positive 1 here for the upper end, the maximum. And for sine inverse, it's kind of the same trick as before. We just interchange the roles of x and y's if we were talking about the inverse. So arc sine has domain. You literally pull out the range of the original function. So the domain is from negative 1 to positive 1. And we can read it off the graph. It goes from -1 to +1, certainly. And the range goes from -π/2 to +π/2, and that was the domain of the sine inverse function. So these are the new functions that we're going to work with, but really what it boils down to is a big review of the unit circle diagram, just like we were looking into in sections 5.2 and 5.3. So even though it looks like a really technical section, it becomes in practice a kind of big review section as well. Oh, sorry, I went over by about a half a minute. Sorry about that. Well, any last questions or comments at all, folks, before we call it a night? Okay, have a great weekend, everyone. Sorry for calling for questions right after class ends. I don't think that's a really good way to ask for questions. But when we come back on Monday's class next week, we'll be right here just working through these kinds of problems. It'll feel like you're doing section 5.2, section 5.3, but you're doing backwards. You're literally inverting what you did in those prior sections. But take care, folks. I'll see you all next week.